right. Hi, everyone. My name is Morgan Bazalgette. We'll be doing a workshop today, as you might have gathered from the notes, about how to build Web3 chess server in Web3, and specifically on blockchain and programming language we're building. If you want to follow along, I shared the link to the repository, which will be scattered throughout the slides. So if you can't catch that now with a picture, I'll pop it up later. If you want to follow along on the slides, they're also there. I haven't linked these up. These slides were assembled in a bit of a rush, if you'll pardon me. But I hope we can still have a blast nonetheless. Just first thing first, I'm going to talk you first through how this is roughly going to be structured. So we are going to have 3 interactive sessions. So it's gonna be divided essentially in 3 small tutorials, let's say. I'm going to do a bit of presentation about what we're doing and how you can build things on top of the programming language we have, which, by the way, is an interpreted version of Go, which is why we're here, basically. In each section, like you'll have some code and you'll be able to play around. You don't need anything special to follow. You just need your laptop. We have everything set up on Gitpod. So as I'll show you, you can just go on our repository and hit the Open on Gitpod button to get started. Goal for today is to give you a full understanding of our programming language and our platform, and see how it can enable you to build services and real-world platforms using Web3. Though I must warn you that right now we're still pretty much in a very alpha stage. In the blockchain world, we call this as not being in mainnet yet. We're doing testnets. And you can essentially see that in the Web2 world as we're just being alpha, right? So we have tons of bugs everywhere. We are entirely open source. You'll have links to our repository at the end of the presentation. Yes, I'll show you later other ways you can contribute. With the variant of the code that we'll be building today, we'll also be holding a raffle. So we have a website where we built like a fully fledged dApp on which you can play chess. You can engage with the platform and contribute also to the development, and that will gain you entry tickets for participating in the raffle. But more information on that later. We'll also have a booth here at GopherCon, so you can come and talk with us later. After the presentation, there will be around an hour to stay a while and ask questions and chat a bit with us. If you need any help during the tutorial sections, there's some of our staff members and engineers scattered around the room. There's Manfred down there with the Gno hat, and there's John. There's John down there. You can help you out. And with that, let's get started. So, what is Gno? Just needed to set that up. So, Gno is the name of the project, which comprises mainly of 2 big moving parts, which is Gnolang. You can see what that's inspired from. So which is an interpreted version of the Go programming language, and it's specifically designed for Web3. And it's like, as I said, it's interpreted, so it just runs the code. It just runs the code directly. We needed to build like an interpreted version of the programming language, and have it different from Go, fundamentally because in the blockchain world, you will have the code. The code will be run by several hundreds of validators, which will need to make sure that the code runs exactly the same. So what we need is complete determinism every time that the code is executed. Together with Gnolang, we have Gno.land, which may be a bit confusing naming, but by the way, that's also the name, like the URL for our website, if you want to check it out, where you can find more information about our project. But aside from that, that's the name of the blockchain we're developing. If any of you know anything about the blockchain world, it's based on Tendermint 2, and it was founded by Jay Kwan, who has previously created Tendermint and Cosmos. Our chain is secured by proof of contribution. So if you know a bit about Bitcoin and Ethereum, you may know that Bitcoin is based on proof of work, while Ethereum is based on proof of stake. So it's a bunch of buzzwords right there that you might not know of, but essentially, like, Bitcoin is famously an environmental disaster because it requires all the machine running on the blockchain network to do a lot of computational power in order to continue the blockchain. It's more complicated than that, but the rough idea. While other chains that don't use proof of work, like Ethereum using proof of stake, or many other chains being developed in the Web3 world, including us, don't use that, and instead we use proof of contribution, which is a variant of proof of authority. If, again, you know some of these buzzwords. And the idea of proof of contribution is that the blockchain is not necessarily governed and controlled by the people who own the most capital to run servers and to run validators, but it is instead primarily governed and controlled by the people who have contributed to it. And that includes a variety of ways. The main one is, of course, writing code, but it's also about writing documentation and, in general, contributing to developing the entire ecosystem. So we are planning to build like a platform where we are developing a platform where you can submit reusable code, and the idea is that all the contributions that are done to enlarge this ecosystem will be rewarded on chain, also, you know, with the token that we have. And yeah, then the grammar of the programming language is identical to Go 1.17, so we still don't have generics. We are still in talks and decisions about what to do about generics. And as last item saying, we don't have things, because of determinism, we can't have things that you may be used to, like network access or file system, unsafe, time.now. Is another one. We'll get into that, but there's a bunch of things that are a bit different from what you may be used to from working with Go. Let me get started on, okay, here we are. On one of the first things that differentiates us from Go. So we introduced a distinction in our programming languages between packages and realms. They are from the code itself, they are similar. What changes is the import path. In the first tutorial, we'll be going with a bit more detail about how this changes. So one has Gno.land/p as the beginning of the import path, and the other one, and the realms have Gno.land/r. The key difference is that because we can't have, that packages are meant to be reusable pieces of code, which you use to build your applications on top of, while realms instead are your end-user application. And for that reason, they support something which is not standard in Go, and that is storing and recovering global variables. So you can see here that we have on this sample realm, we have a sample counter, a counter program. So on the Gno.land chain, like this single file already creates what's called as a smart contract. For those of you outside of blockchain, again, a smart contract is essentially a program that runs on the blockchain. There are currently on the existing blockchain a lot of domain-specific programming languages for this. Some blockchains also, because they're based on bytecode, they have like LLVM compilers which go from Rust to the blockchain's bytecode. But instead, what the approach we're taking is that you can only upload directly the source code of the smart contract on the chain, and so you can't upload a compiled version of it. And that is a feature in the sense that we are very, very strong on open source, in the sense that all of our software that is going to be uploaded on the chain is going to be open source and verifiable. The functions that you see, the exported functions, will also thus work as like end user, let's say RPC endpoints. You could call them like that, or API calls, in the sense that, as we'll see later, you can use one of our command line tools, or in general, one of our API clients, to connect with the Gno.land RPC node and make transactions with it. And so in this example right here, if we call the increment function a bunch of times, like this counter will pop up. But what you may not be used to from normal Go is that you may think, okay, I'm running this program, and well, first there's no main function, so how's this going to work? But secondly, like, you know, even if I were to run this program, so run increment, like every time I run it, like counter would still be set up to 0, and so it would go to 1, and that's about it. And as we'll see later, because the global variable is stored within the data of the blockchain, like that is what you can essentially use as a data store, as a database for all your information. And it is where we'll be storing our chess games and information about players and everything else. Next up, I'll be shortly introducing the dev tools we'll be using today. So we have like the command line tools. We have two main ones, which are Gno and Gnoki. Gno is quite similar to the Go command line tool you may be used to. So it has things like go doc, go run, go test. It also has a REPL, like Python, because as I said, we're interpreted, so you can simply run expressions and it'll execute them for you. And the Gno command line tool is meant for local development and is being developed with the idea that it is not necessarily to be attached to a blockchain. Like, we're still working on developing this, you know, with the idea that we're going to use this on the Gno.land blockchain, but it will not be the only chain that will be using Gno, or possibly the only application, you know, blockchain that will use the programming language. Like, if there's anything else which might need an interpreted language with perfect determinism, like, we're building just that, and you can reuse that code for whatever purposes may be. And together with Gno, again, we have Gnoki, and that's what we'll be using for the more blockchain-specific part. So you can use that essentially to upload, let's say, your contract to the blockchain. So in the Gitpod environment that we have set up, the local development blockchain will be set up right into your browser, well, on Gitpod server, connected to which you'll connect through your browser. And you'll be able to call that, and as we'll see, also interface yourself with the web sort of front end that you can use to play around with the realms. Then, yeah, as I said, we're gonna have a few sections for our workshop today. So the first section is going to be about getting acquainted with these two command line tools and publishing our first realm on chain. So a gentle introduction to using the platform. Then in the second part, we'll get into what you're probably here for, and which is the chess server, and we're gonna look at how we can write a move validator. Then in the third and last section, we're gonna look about how we can create realms to actually build up the networked chess server. So not just the move validator and the chess engine that we're building with it, but also how you can have players interacting with each other and playing chess on the blockchain. Each tutorial should be around 15 minutes. This should have been changed. And you don't need to have completed the previous section to participate in the one after it. So if I start again with the presentation, don't worry. Each section is not dependent on the previous one. And this goes also if a friend of yours is joining in late. They can just pop in on the repository and they'll be able to just jump right in. And yeah, there's also like solutions to every interactive part that you can use to in case you're stuck or you want to see a reference implementation. And as I said before, since we're developing, we've developed also like a full website and like much fuller realm to play chess, which does all crazy things that if we play chess before online you may be used to, which are like leaderboards, ratings, and all that kind of stuff. It doesn't do chess engines. Like you can't have Stockfish on the blockchain. Well, at least that would be complicated. But yeah, this is roughly how it's going to work. So with that, I'll shut up, and we can get started. So if you go on our repository right there, github.com/Gnolang/Gnochess. You can find the README with the Open and Gitpod button, and you can get started by. I'd recommend you follow the first tutorial, which is linked in the README, side by side with the Gitpod you'll be opening. So just. I'll show you briefly how that looks like. So as I said, you have Open and Gitpod here, which you can open. It may require you to sign up, but it should be a straightforward process. You can just sign up with your GitHub account, and it will give you access to create an instance free of charge. And then down here, there's a link to the first tutorial, which you can click on, and it'll tell you how you can get started playing around. So I'll leave you be. If you need any help, I'm here, and my colleagues are here as well to help you out. Right, so I'm gonna get started with the next section. I've allowed for a bit more time as I was just following along to, sorry? What? Okay. Can you hear me? Okay. Sorry. I just allowed for a bit more time as I was just following along and seeing what point of the tutorial folks were at. So we'll now get started with the chess part of a workshop. So in order to play chess on the computers, as you may know, we'll first have to do some transformations, you may call them. So we're going to have to go from the physical board, right here, which is very hackable. Like there is no legal move validation. So literally, like you could move your pawns anywhere. So we're going to transform that first into like a grid of squares, which is what some of you might be used to if you ever played a chess online. And we're essentially going to trim that down to a very simplified version where we have like just the pieces represented as, well, byte values, small byte values. So this is like a general idea for how these chessboards convert. So one of the things we'll see like, for instance, standard chess notation, which is called FEN, which is used like to share chess positions throughout chess platforms and chess programming. And so one of the conventions that, that first we have is that if you have uppercase letters, then it means it's a white piece. And if you got lowercase letters, that means it's a black piece. And then you have like the pieces represented as the classes of pieces, the underlying classes of pieces. So rook, knight, bishop, queen, and king. You'll see that the knight has a conflict with its initial with the king. So for simplification in chess notation, it always gets its second letter N instead, but all the rest should be fairly straightforward. So just a quick recap, just because I'm not assuming you know any chess before heading into this, although you know you have a rough idea. So each piece in chess has different move sets, as you may know. The pawn move forward, so technically towards the opponent's end of the board, and they cannot capture forwards. So that if they hit another piece like in front of them, they cannot capture it, and they have to capture diagonally. And additionally, the pawn is actually surprisingly the most complicated chess piece that you can have, because at the beginning it can go 2 squares up. It can do like this very weird thing that many people who don't play chess online are not even aware is a thing, which is called en passant capture. But feeder rules, which are the way that chess has been played, especially competitively for the past 150 years, include this rule. Then there's promotion, which is when a pawn gets you to the other end of the board, and it must change into another piece, which can be a queen, a bishop, a knight, or a rook. The rook moves horizontally and vertically. The knight moves in L-shaped patterns. I'm assuming you know what I'm talking about, but essentially, yeah, like 2 squares in one direction and a parallel direction of 1 square, or vice versa. The bishop moves diagonally. Some of you may know that, yeah, with the like games that are based on a square, like diagonals seem like a bit of way of cheating, because you're not traversing like 1 square, you're traversing the square root of 2 of squares, but that's besides the point. The queen combines the powers of the rook and the bishop, so it's able to move like both horizontally, vertically, and diagonally. And finally, the king is able to move 1 square in all directions. It can do like this crazy move called castling, whereby it can move, if it's in the starting positions and it has not moved together with the rook we're castling with, then we can like swap them out, so to speak. And what that entails is that you move the king 2 squares towards the rook and move the rook alongside it. And additionally, one last very important rule is that the pieces can't move. Like you can't move a piece and have your king be in check. And what it means to be in check is for your king to be attacked by your opponent's pieces. I'm a bit confused. Okay, so the thing is that when doing chess programming, we cannot just determine like the validity of moves based on just the current board alone. And this is true also when you're playing chess with someone else. So you actually need to have a bit more context when you're playing with someone else to know if the move they're making is legal or not. And the reason for that is that, as I mentioned before, for instance, castling is only available like if the king or the rook hasn't moved before. So the idea is that even if the king goes back into its original position, if it has moved, it cannot castle anymore. So we need to store that information. And another information we need to store is about en passant captures. So en passant captures are like this crazy thing whereby if you get on the if you get on the sixth row, imagine you're white, and your opponent moves a pawn forward too, so you'll have the pawns in parallel like this, and you can do a capture diagonally of your pawn of the opponent's pawn, but it's the only capture in chess which is not actually having the pawn take the position of the other pawn. It's a bit weird. I can show you that if on Lichess if you have questions about how that works in reality. And then finally, one other thing that if we want to build a full chess engine, we must add. So we have the endgame conditions. So there's one that everyone knows about, which is checkmate, which is when the king is under attack and it cannot it cannot move anymore, and there are no legal moves to prevent the king from being under attack. And additionally, the second most well-known rule for endgame conditions is the stalemate. So the stalemate is the sister of the checkmate, with the difference that the king is not under attack. And the idea there is that the player at that point has no more legal moves that it can do, but it also has the king which is not under attack. And if you ever play chess online, that's actually, there's some end games which this can very easily happen, and you're very frustrated when this happens because you may be winning, and then at one point the game just tells you, oh, it's stalemate, and you've just drawn with the opponent, even though you might have been an advantage. And so and additionally, there's some other draw conditions which make chess a finite game, so you can't go on infinitely playing chess, which are the 75 move rule. There's this terminology in chess like what is a move and what is a half move. So a move is actually 2 turns, so black and white playing, and a half move is just white playing or black playing. So 75 move rule actually refers to 150 half turns, half moves or turns for each player. And if there's 150 half moves between the 2 players, and none of them has moved the pawn or captured another piece, then it's an automatic draw. This is also in tournaments, although that rarely ever happens, like in competitive tournaments. And there's a variation of that, which is the 50 move rule, which means that at 50 moves or 100 half moves, then one of the 2 players can say, okay, this is a draw, and it's automatically a draw. Like, it doesn't have to wait on the other opponent saying yes. As you may know, like there's also the rules allow for resignation and for drawing by agreement. So we just shake hands on it, essentially. And then there's 3- and 5-fold repetition. This is the last one, whereby if you have the same position in the chessboard occurring 3 times, then as before, you can declare it's a draw without waiting for your opponent to say, yes, it is. And if it happens 5 times, then it's automatically declared a draw. So that's it for the chess rules you may not know of. Hopefully you learned something today. But we're going to go ahead and talk a bit about how we're going to program this. So the chessboard is an 8x8 grid, and we got 6 classes of pieces. And I added there a ×2 because we really have 12 if we want to count the classes of pieces for white and for black as being separate. It's mostly relevant. It changes just like when programming just for the pawn movement, because the pawn moves forwards and you need to know which color the pawn is to understand what forward actually means. On the back end, we don't need to implement like full move generation, although actually we kind of have to. Sorry. Yeah, I got messed up. On the back end, we only implement move validation, but we will have also to implement like a move generator. And the reason for that is that we need to understand if a player is in check, to understand if the move is legal. So it's gonna be more complicated than just making sure that the move is within the piece's moveset. And so what we're doing today essentially is creating a full-blown chess engine. So imagine Stockfish. The thing we're not doing is that we're not doing like searching and position evaluation. So the way that chess engines typically work is that they have this recursive like search algorithm whereby they list all the legal moves from a position, and then they branch off into doing a search into each of these moves, and go on up to a certain depth until they find either an endgame condition like a checkmate or stalemate, or after a given depth they just give up, and then there's an evaluation function which says which tries to guess using an algorithm whether it's winning for white or winning for black, and so those tends to be like the parts that we're not going to do today, but which separate us from being a chess engine. There's also a notation that we'll be using for programming, and that will be useful for our testing, because most of the sort of benchmark tests that you can find online to check whether your chess engine is performing well or not use this four-synth Edwards notation. So this is actually slightly more straightforward than it may look at first glance. So what you have here is the representation of the board, this very long string separated by slashes. So each slash separates like each row or rank of the board. And whenever you have like a letter, like is what I was telling you about before. So R means a lowercase r means it's a black rook. Lowercase b means it's a black bishop, and uppercase P means it's a white pawn. And then you have the numbers in here. So the numbers mean that between these two pieces, there's an empty square. And so this represents the entire board. For instance, this /8 is an entire empty row. Then we have the player to play. So this is, if I can read correct, well, actually I have it here. It's black. Then we have, as I was mentioning before, you have also to store the castling rights. So KQ, uppercase KQ, lowercase kq, means that both white and black have maintained their rights to castle kingside and queenside. And if one of the letters is not present, then it means that the respective color has lost the right to. Then we have this dash here, which is like the null value in this notation, which is used to store the n% square. As mentioned before, that's another of the things we need to store. And then we have the half move clock and the full move counter. So the half move clock essentially tells us how many moves it's been since the last pawn capture, since the last capture or pawn move. And it's what I was telling you about before. So when that reaches 150, then it's an automatic draw. And the full move counter, that's just aesthetic, and it just means how many moves into the game we are. And yeah, that's what you need to know in previous knowledge for doing some chess programming, like at least part of it. You can learn more, of course. If you don't know, people have been going around chess programming basically since the start of computers. Because if there's one thing that the nerds love, it's chess and computers. So you have the chess programming wiki up there linked. You can find it on the slides as well. And if you click on the chess programming on that link, you'll find a full wiki with all kinds of different algorithms that have been implemented to try to optimize and essentially build the fastest chess engines possible. And there's some very crazy tricks out there. One thing that is done, for instance, that we don't do here, and for the sake of simplicity, is what are called bitboards. So instead of representing the board, as I mentioned before, using an array of 64 pieces, the way that it's done is that information is stored in many unsigned integer 64s, which store bitwise information about various things, like where is this piece attacking, and through using bit manipulation, you can actually be much faster at what we're doing today. But for the sake of this presentation, we're going to skip on that and skip on the last 20 years of chess development. Well, 40 years, I guess. And we're just going to go into a much more simplified version of this. This is a quote from Linus. If you never read that, will in fact claim that the difference between a bad programmer and a good one is whether he considers his code or his data structure is more important. Sometimes true, and I think like the reason I'm doing this slide is mostly to give you like a taste for some of the for the tutorial that we'll be doing. So I've taken some decisions on the data structures, a bit arbitrarily, you might say. You may not agree with what I did, but I don't care. So I'm just going to walk you through this one and explain things a bit, so you can get around playing on the second tutorial, possibly without feeling too much confused. So as I said, we'll be storing the board as an array of 64 pieces. That's just, as I said, to try to keep things simple. The piece is just a byte value, which can be a piece empty to mark as a 0 value to mark that there's nothing there. Then piece pawn, piece rook, piece bishop. We also have piece black, which is a bit flag. So if you OR that into the value of the piece, then you can essentially convert the color. Then we have the position. I'm going to simplify again here. So technically, like we would have another couple fields here, which are the half move clock and the previous position hashes to implement like the endgame conditions I was mentioning before. So we're going to skip on that for this tutorial and instead just talk about the board, take as input the board, the move, and some position flags, which are for the n% column and the castling rights. Next up, we have a way to represent the move. So in order to store the information about each chess move, we're going to store the square it's moving from and the square it's moving to. And additionally, we're going to store like the promotion. So when the pawn moves to the end of the board, it can change into queen, bishop, a rook, or knight. And so that's it. That is where we're going to store that. If it's not promoting, then we'll set that to 0. We'll be using a slightly different notation that if you played online to what you used to. So what is generally used is called the standard algebraic notation. So it's like qx c4 to say that queen took on c4. That is actually very like it's another programming feat to implement a parser for that notation. So we're going to skip on that and instead use a simpler notation, which just maps onto this the structure, which is actually used like in chess engines and other places, which has the name of long algebraic notation. So just the 2 coordinates and any promotion. So for instance, a1, a4, c2, c2, d5. And if we're promoting, then we're going to have something like d7, d8q to say that the pawn has promoted to a queen. Finally, we'll have as another data type that we'll be using the square. So different from position. The position like is the board and the other information about the current state of the game, while the square entails what specific square of the board we're looking at. So this is a value from 0 to 64, and the lower 3 bits encode the column or file. So in chess we have like instead of saying rows and columns, we can say ranks and files. although I'll mostly be using rows and columns mostly for the uninitiated. And then we have the bits 6 to 4, which are going to be storing the row. So these are like, there's 8 rows and 8 columns. So 3 bits, 8 values, so it maps 1 to 1. With that in mind, I think we can move on to the second tutorial. And so we're going to be writing a move validator. This is going to be like a big fill-in-the-blanks tutorial in the sense that when you're not actually going to be building a move validator from scratch. The reason for that will become apparent, like it should already be apparent from what I talked. It's actually, you know, not something you can do in like 15 minutes. In fact, it's taken me probably a week. But I sort of trimmed it out a few parts so you can still like play around and see how you would go around doing that, at least with this simplified data structures for chess. So if you're just joining in, you don't need to have completed the previous part of the workshop. You can just jump right in and go on the GitHub repository that we have right there. If you click on Open on Gitpod, you can start hacking right away. And that said, there's the second tutorial in the tutorials directory on GitHub. And now I'll leave you be. Have fun. Right. So, sorry if any of you guys are still working on things. I know that this tutorial may take a bit more time. In general, like this whole thing was trying to condense like a lot of work on what is actually a large task in programming in a very small workshop. But of course, like everything will still be online after the end of the workshop. So if you're still interested, and if we piqued your interest with what we did today, you can just follow along at home if you have the time and are interested in what we're doing. There is a work in progress last part of the presentation that I would have liked to do as the third section of the workshop today. We kind of scrambled to get this done together by today, and mostly because of the website on which we'll hold like the game and subsequently like the competition, quote unquote, that I'll talk about later. So I'm just quickly going to go through like how you would go about creating like the server part of the chess server. So combining like the first part about uploading a realms and having the realms on the blockchain to be able to and interact with them and playing a chess server. But we're not going to do a tutorial section for this one. And yeah, I'm just gonna go right through the end and then take any questions. So I don't know if any of you have seen this. It's a wonderful video by Tom Seven about creating weird chess algorithms to create bots that play chess, which are bad, which are more satisfying to play with than chess bots, which are good, because they generally tend to beat you. I don't know if any of you has tried to play against Stockfish. It feels really bad for your self-esteem. But besides the point. So if you want to play, you're going to want to play with someone else. So in order to do that, we can work out some realm functions that we can just call from Gno.key after this. And actually, we can call from web apps as well. We have a JavaScript client that you can use to build web apps. And in fact, it's the one I will show you quickly afterwards. So this is I'm just running through a small example of like a function that would run here. So as I said, most of the functionality that Gno gives and that enables you to write like actual backend applications with this is about storing data in global variables. So here we have like this variable game store. Now you can't see my highlighting, so I'll go here. So you should be able to see it. So you have this GameStore.set down here. And this is essentially the part that's doing the magic. Well, as well as get user games. These are all functions which are calling on the global variables that is stored within the realm. And so they get data about the player. If you see above here, we have in the function declaration the caller and the opponent. So we're getting information about the caller and making sure that it's not got any open games. So you just avoid having games being played in parallel, avoiding that the caller playing with itself. You might notice something which is a bit different to what you might be used to in Go. So in Go, you tend to handle errors by using Go's typical error handling. I'm sure you're all familiar with if error is not nil. Here, we're much more fond of panics, and there's a reason for that. The reason why we like panics so much is that we introduce unrecovered panics essentially as our feature to abort a transaction. So essentially, on the blockchain, like you will have every node, every validation in the blockchain will have a full state of everything that's happened. So if you wanted to play chess with the chess realm that we're building today, you could go at any one of these and ask, hey, can I make this move? And as long as you have an open game with an opponent and you pass the right parameters, it will happily do that for you and distribute that information to all the other participants, validators in the blockchain. But if you have a panic, then that completely aborts and says, no, like this transaction is invalid, so we should not distribute it to everyone else. Like this should not be recorded. And this is useful also because like we have a conception, like we have a concept of gas, which is like it's in order to perform things on the blockchain, you need to quote unquote pay money. So you need to pay some tokens of the blockchain's native token, in our case the Gno, in order to perform the transaction. And you know, I think this is one of the aspects of Web3 that many people that first hear about Web3 go, what? Like, yeah, now I have to pay to use the internet? Like, is that what you're proposing? Like, the alternative to Web2 is to just paying for using the internet? Just give me advertising, please, right? I'm going to talk about that in a second. Why, like, paying for what you use on Web3 is potentially a better model than what we have on Web2. But yeah, so the idea here is just that, you know, we create a game which is which we still store it as a pointer. This way, after we store the thing in the game store, like we can retrieve it back from the game store. Imagine game store as being a fancy map, right? It's called an AVL tree. You can kind of see it as an ordered version of a map, which sort of performs better for what we're doing and what we're accomplishing, and for like building maps which potentially have thousands or millions of entries. And so this is an example instead of the make move function, which is used on from the chess realm to make a move. So again, my scrolling doesn't sync from the speaker view to your view, so I'm going to have to bend over to the screen to see what I'm doing. So again, we have like what you would expect from some backend code. Though I think like before working in blockchain, I used to do a lot of full stack development and working a lot on backend servers. And honestly, not dealing with HTTP requests all the time kind of makes this feel a bit more pure to me. Like I'm actually just working on the code and the logic rather than working on you know, parsing HTTP requests and everything else. We have a bit of bureaucracy here right now, which is annoying. And if you see the full chess realm that we develop, you can see what it is, which is we don't currently have features like reflection, which entails that nice things like JSON marshalling are simply not there yet. So you have to build JSON marshalers by hand, which is what I had to do. But as I said, we're alpha. We're aiming to launch like within the next year, possibly. We're not giving exact dates, but if you want to follow along on the ride and even help us out, I'm going to give you some info on how you can go around doing that later. But yeah, so as I was saying, we can get game here. This is just a helper function which calls the game store I was referring to before. And as you can see, we don't need to put the game back. Well, we have this save result down here. Actually a bit different from what it looks like. It doesn't store it back into the realm, because just updating the value at the pointer, because it's a pointer, like the value will be updated, and so like the GNOME VM keeps track of all the objects that are around, and so just performing this transaction and changing g.state is automatically like committing the value to a database. Like you can see gstate equals game state drawn 75 move as being like effectively an SQL query in Web 2. And yeah, so for the brave of you, there would be like a third tutorial, which is very, very rough. I'm not going to take a break for this. If you want this, like it's an exercise for the reader, I encourage you to try it out at home. But we won't have time for that today. And now I want to ask the question that maybe some of you were trying to answer in the moment that they decided to participate in this workshop, which is, why the hell would you build a chess server in Web3? And the short answer is, we don't actually need to build a chess server in Web3. This is mostly like an experiment, and it's an educational tool. But I think there's something to be taken away from here, which is larger than this. Because chess is probably not the most ideal application for what Web3 enables us to do. Let me just go through here. So what we can have with Web3, which significantly changes from Web 2, is that the code and applications that are uploaded to the chain, they are not bound to some single individual or some single company paying for the server. Like for chess, this doesn't tend to be much of a problem. Like we have two big chess servers. One is a bad one, closed source. One is a good one, French and open source. So the good one is Lichess. The bad one, I won't say the name. But so we already have those, and they seem, and they're sort of financially stable, and they work. They're free. Something which a production chess realm couldn't say it's doing. But the advantage that we have is that the code that is published here, whether it's chess code or whether it's code for any kind of other backend server that you want to build a Web3, it will outlast you probably, because as long as there's people participating in that given blockchain, then the code remains there, right? There's a given block with your code. It's stored there. Every person, every move that anyone's ever done is stored permanently, which is kind of extreme for cases like this. But I think we can agree that there are some cases where we would actually like that. Just going over what else we're saying about on this slide. So we're like the mantra of blockchain, I think, from the very inception of Bitcoin, is that we're trying to achieve trust in a trustless environment. And as you may know, like the thing about backend servers in normal Web 2 is that, say for instance, like even messengers, right? The problem about messengers and why we focus so much on end-to-end encryption is that you never have a way of properly verifying what the code that is running on the backend is. Like you simply cannot do that. Like it may be an open source, servers like Signal, which provides like the backend code, and you can inspect it and make sure that it's working correctly and encrypting your data. And sure enough, because of end-to-end encryption, like you can be pretty sure that it's not reading your messages, but it will still, like, it still has the potential to record metadata and, you know, have all these privacy issues. And of course, like on blockchain, this issue is not solved for direct messages specifically. Like, everything's public on the blockchain, so direct messaging is not a good application for what we're doing here. We're talking more about like forums where the data is meant to be public. So the thing that we're taking this to the extreme because we're developing on what Ethereum has done. So Ethereum, you can upload. Imagine like you can upload a jar file to the blockchain and execute it. It's just that tends to be like it using instead of the EVM bytecode, which is a different bytecode with simpler instructions, and which shares many of the features that we have, so complete determinism, so it can be run everywhere. But yeah, let me get back on the games that we're talking about. So I'm sure many of you are somewhat familiar with this game, Club Penguin, and its demise. So this is the thing about online communities, that they are very much bound to whoever is hosting them. Like, you cannot, like, when Club Penguin, like the demise, the fall of Club Penguin, and they shut down its services, has been kind of catastrophic, as it had an incredibly large user base. But when the company decided it wanted to shut down the service, the game, like, there was immediately nothing that players could do. Then, you know, private servers spun up, and it tends to be the case that, you know, in games with very, very, very large player bases, like things like private servers start showing up. But if you have things like, say, World of Warcraft, where people spend maybe thousands and thousands of hours building up on this game and building up all the things that they have. If the company that's supporting the game decides that it's not profitable anymore, then it just gets shut down for eternity, and there's nothing the players can do about it. And I think this is one of the applications where we'll eventually like see better like where Web3 will be able to solve some of these problems, because it means that these games can be effectively run in eternity. And part of the reason for that is because the users are paying for the service to be up. So remember before when I said that yes, you would need to pay for the transactions in order to execute them? The goal there is, well, that, you know, it may sound weird that we're going from the free and open internet to being an internet where to do anything you have to pay this virtual magic digital money. But that means that we can actually work towards a more sustainable model for the internet and open source, which is, you know, part of what we're doing as a project. We want to reward, like, what we're talking about proof of contribution. Like, that's one of our takes on how to solve like the chronic problem that open source has nowadays. That open source contributors are constantly, open source like maintainers are constantly like having to beg for money from big companies who are using their code to massive code bases, making trillions of dollars, but they're seeing about a very, very small fraction of that. So that's an unfair system, and it's unsustainable, right? So how can we improve this? How can we both solve the open source problem and solve like the durability problem of Web2 applications? And our answer to that is, well, you guessed it, Gno.land. I'll get on with something with the next part. So I don't know if you ever read the Bitcoin white paper. I recommend you to. It's not long. It's also a nice read, I find. And I think the abstract is already like quite an interesting part to just read through. You're not going to have to read that. I quit it over. Just in case you've never seen this, it's a wonderful blog about all the startups that have failed and the services have been shut down for their users. Like, it's been updated for about, I think, about the last 15 years, and it's got like hundreds of posts about services which are just shut down after an acquisition. Like, we're not even talking about running out of cash, just acquisitions and then blog posts, our incredible journey, haha, see you next time. And the service shutting down in 12 months. So the Bitcoin white paper essentially starts off in the abstract about saying transactions in the digital world are inherently flawed because they need to be centralized, and whoever's taking care of doing the centralized servers, whether that be Visa or MasterCard, like they needed to take a transaction, and they can't help but they can't help taking a transaction because people will expect these central authorities to be able to handle support and to be able to make sure that their transactions are valid and so on, and manage both the infrastructure, but also all the complaints and also all the fraud that goes on within the digital financial system. And so that is one of the first things that spun out the development of Bitcoin. It was not creating a speculative cryptocurrency market. Like, blockchain is so much of a larger project than just cryptocurrency speculation. And our project, we believe, is so much bigger than just cryptocurrency speculation. And yeah. So for us, the answer is that, yeah, with blockchain, what we can have is to achieve trustless in a trustless environment. And we're building on top of that to make it so that we can have perpetual applications which are not bounded to just some company still having money and having to make a profit essentially out of and I think if you want to see it being maintained and working, and also enabling a fairer model for open source contributions. All right, that's all for today. I kind of overrun on the last part. These are all our links. There are quite a few. Sorry about that. We'll still upload all these slides and all this content after in a few days, probably. As I said, we have been doing this in a bit of a scramble, so it's kind of like I was working on the slides about 10 minutes before coming in here to talk. If you're interested in contribution, it's not just when we're going to be like as we said mainnet that we want to reward contributions, but we're also rewarding contributions right now. So if you want to find out how you can contribute and get rewarded economically, there are some links there that you can find. And we're hiring. If you're looking for a job, there's Samantha right there who has a Know Who's Hiring T-shirt who you can talk to. And finally, we are holding like a raffle. So if you go on the Gnochess.com website, I'm gonna pull that up just here. We have developed like an application where you can come and play with a fancy 3D gopher in the background here, which we're very proud of. A big shout out goes to our designer and front-end engineer, Alexi, who is not here with us today, but who has done a massive job at getting this out the door, as well as my colleagues, Milos, Michael, John, Manfred, Ballet, and everyone else who has helped this push out the door. It's been a crunch for the past month, but we're in a roughly stable state where we hope you can sort of play chess games against other people and have some fun. Also, like we have on, we're going to hold a raffle, and to see more information about how that's going to work, we have this file right here you can check out. So we're going to award some points. So every point will be an entry. Yes, I'm coming to that. If you want to register and come and participate, you can come to talk to us later today, or you can come at our booth tomorrow. That's it. Overrunning. If there's any questions, Vale will be around too with the microphone. So please go ahead and ask.